Good morning, guys. So today we're going to be reviewing the midterm exam study guide. Okay, there's a disclaimer on top to just remind you that the exam will consist of 25 multiple choice questions and you must answer 3 open-ended questions, which should take about 1 hour. The second hour of the exam will be project-based. If you're in an A-day class, right, on A-day on Monday, we will physically begin that project-based design. And for our My B-Day students, you guys already have your blueprints made, and you guys are going to finish those up on Tuesday. Okay, so the study guide is comprised of 3 major topics. We're going to begin with units/vectors. The substitute should have handed you out a physical packet if you are in class. If you are remote, I had asked you yesterday to print out the study guide. If you did not do that, please pause the video and print it out yourself. Okay, so our first unit, we looked at the math required to learn and understand physics. Okay, so SI units for the following quantities. So SI units meaning the metric system or the system international units. For mass, we measure mass in kilograms. We're to use the abbreviation kg to represent. Distance, we measure in meters. A lowercase m is the variable we use to represent that. Time, we measure in seconds. Lowercase s is our variable. Velocity, we measure in meters per second, which is lowercase m slash or divided by s. Okay, force we measure in newtons, named after Isaac Newton, and the variable we use to represent that unit is a capital N. Acceleration we know is the rate of change of velocity, so the units for acceleration would be meters per second per second. It tells us how the speed changes per second. Within this unit, we also talked about unit conversions and SOHCAHTOA. So we're going to do a few examples together right now, and then you'll pause the video and take a look at the remaining examples. So in the following problems, we're asked to convert the following quantities to SI units. Okay, so to convert to SI units, we need to convert to these units that we listed above. So I'm going to start with number 7. We have 2 hours and we need the SI unit for time, which is seconds. So we need to convert hours to seconds. You'll notice on your equation sheet, okay, in Google Classroom, which is behind the homework list, you have all those equations or common factors. Okay, so we know that there's 3,600 seconds in an hour. To get rid of hours, we need hour in the denominator so that it will cancel out. So the old unit goes in the denominator and the new unit goes in the numerator. Okay, we know that there's 3,600 seconds in 1 hour. When we plug that into our calculator, 2 times 3,600, we get 7,200, and our units are seconds. So that is our final answer. Okay, so that is single unit conversions. Single unit conversions. We're going to skip down to number 9. In number 9, we have a unit rate. So we have kilometers, or sorry, in this case, we have miles per hour. In number 9, miles per hour. So I always like to rewrite these as a unit rate, so it's a little bit easier to picture. MPH is miles per hour. Okay, to get rid of our miles, we need miles in the denominator. Okay, for distance, we need meters. So we're going to need meters in the numerator and miles in the denominator. Hours is in the denominator. So we're going to need hours in the numerator so that they cancel out. Just going to color code this a little. There we go. And our metric unit for time is seconds, so we're going to need seconds in the denominator. What that's going to give us, okay, we'll see that hours will cancel, miles will cancel, and we'll be left with meters over seconds. Now we just need the conversion factors. Okay, in 1 mile, we have 1,609 meters. Okay, and in 1 hour, we have 3,600 seconds. It's a popular one, popular conversion. So we're going to multiply straight across. We have 75 times 1,609. Enter in your calculator. Divide that answer by 3,600, and we will get 33.5 meters per second. Okay, so units cancel out. Okay, just like variables in unit conversions. What I want you guys to try is 8, 10, and 11, and check your answers with the answers posted in Classroom. So pause the video, try 8, 10, and 11. If you had trouble with any of these, this is obviously from our first unit, so you want to take a look at the metric conversion quiz and the metric conversion homework, which there is a link to in Google Classroom. Besides unit conversions within this unit, we also had SOHCAHTOA, okay, finding the missing leg of a triangle or missing angle, which we review a little bit later in the packet, okay, and converting from metric to metric, okay, which is a similar process here as well. So moving on to our next unit, kinematics. Okay, so this is a combination of both 1D and 2D kinematics within the review packet. In physics, we have different types of quantities which determine or decide how we mathematically can consolidate them. Okay, so with vectors, I'm going to type in here. A vector is a quantity with units, magnitude, and direction. Okay, so with a vector, the direction matters. If we have vectors in the same direction, both are pointing north, 5 miles north, that's 5 miles north, we can add those together to get 10 miles north. If they're in opposite directions, directly opposite directions, meaning that we have something like 7 miles west and 10 miles east, right? We say that east is positive and west is negative. So we have to subtract those two vectors because they are in directly opposite cardinal directions. So we would get 3 miles east. okay, because we've moved more east than west. If our vectors are perpendicular to each other, right, we have to use vector addition, which involves using Pythagorean theorem and finding the direction using trig, which we will review in number 19. Okay, so vectors, the direction matters. If they're in the same direction, we add. Opposite directions, we subtract those vectors. If they are perpendicular to each other, we use Pythagorean theorem and trig to solve. A scalar quantity, okay, for example, speed, is a quantity in which direction does not affect our mathematical process. So basically, it's a quantity with units and a magnitude only. There is no direction. So for example, the most notable example is speed, which is the total distance, okay, over the total time, which we'll get back to in a second. So regardless of the path that you take, your entire distance is added together and divided by the total time. So because the direction is not accounted for, speed is a scalar quantity. Okay, so displacement, which is a vector, so add in V for vector here. Displacement is a change of an object's position. Okay, and the equation that we use for that displacement is delta x, right? That Greek letter delta stands for change. It's our final position minus the initial position of the object. Okay, and direction matters. Direction matters when we're finding displacement. The distance, okay, is a scalar quantity. Distance is the total ground covered. So every step that you take is accounted for in the distance measurement. Okay, and we actually use the lowercase letter d to represent distance. And it's basically the entire path. So we would measure the length from the final position to the initial position, regardless of the path, and that would be our distance traveled. Okay, we'll get back to that in number 20. Okay, S for speed, S for scalar. Speed is a scalar quantity. Speed, which we usually use the lowercase s to represent, but sometimes, depending on the book or who wrote the example, we sometimes see that written as a lowercase v as well, which is confusing, and I don't really like that notation, but you will see it sometimes. So speed is the total distance divided by the total time of travel. Okay, so even if the object stops moving, that time is included in its travel time. So it's the entire distance, every step taken, divided by the entire time it took to move that distance. Okay, so speed is distance over time. Okay, velocity. Velocity is a vector quantity, v for velocity, v for vector. It's the rate of change of position over time. So our equation for average velocity, which is on that unified equation sheet in classroom, it'll be the displacement, delta x, over time, delta t. So yes, we do use delta t but really that time is the total time that is traveled. Okay, so if you stop, just like in a cross-country race, the time that you stop during the race is counted in your calculation of your velocity. Okay, so t, although we use delta, it is technically the time from the beginning to the end of the object's motion, even if that includes a rest or a stop. We know that delta x is technically the final minus the initial position, which we use a motion diagram to help us determine, okay, which we'll review in an example below. Next up, our last quantity within kinematics that we talked about is acceleration. Acceleration is the rate of change of the velocity over time. So basically, it describes how many meters per second the object's velocity will increase or decrease per second. Okay, so from above, our units are meters per second per second. And technically, our equation, it's the rate of change of velocity. Acceleration, we use a lowercase a for. We usually use average. For one-dimensional motion. So the average acceleration is going to be the change in velocity over the change in time. Oh, that did not work out as planned. Okay, there we go. Take two. So our average acceleration is equal to our change in velocity over the change in time. Okay, our change in velocity can be calculated by taking the final velocity of the object, subtracting the initial velocity of the object, and dividing by the time interval it takes for that velocity to either increase or decrease. And that gives us the average acceleration rate, which again, the units are meters per second per second. Okay, so let's apply these concepts to a few examples to kind of refresh our memory. We're going to take a look at, let's start with number 20, actually. So in number 20, we have Karina runs 4 complete laps around a 400-meter track. Okay, so Karina is going to start, her initial position is going to be at the starting line, and she runs 4 complete laps. 1, 2, 3, 4 laps around the track. So that means that her final and her initial position are the same. She's going to start and stop at the start and finish line, which is the same line on the track. In part A, we're asked to find the distance that Nadia traveled. Oh, I should have changed that name. Okay, that's okay. So the distance that Nadia or Karina travels, right? Distance, D, is the total ground covered and includes every step that you take regardless of the direction. So 4 laps of a 400-meter track, every step that she took, okay, would be 4 times 400 meters. So we would get 1,600 meters is the distance. It's the scalar quantity, okay? So because direction is non-essential, we do not have to include it. Or rather, we shouldn't include it. So the distance she travels is 1,600 meters. It includes every step that she took. In B, it asks for the displacement. Displacement is the change in the object's position. It's the final minus the initial position. Around a track, the final and the initial position are the same. She starts and ends at the same position, which we can really name whatever we like. We could call it 400 meters. We could call it 0 meters. 0 minus 0 is 0. 400 minus 400 is 0. Her displacement, her change in position, is 0. She starts and ends at the same spot. Okay, so what that would mean is that her velocity is also 0, because velocity is change in position over change in time. 0 divided by however long it took her will be 0. So when you're running around a track, you have no velocity at all if you start and end at the same place. And you also, if you start and end at the same place, you have no displacement. The last segment of this question here, see if it took her 5 minutes and 40 seconds to complete, what's her average speed? Okay, so speed, what is speed? Speed is the total distance over the total time. The total distance we found in part A to be 1,600 meters, and then we divide by the total time, which in the metric system, we need to be using seconds. So we need to convert minutes to seconds first, and then add the 40 seconds, right? We need one consolidated unit, and we need the answer in meters per second. So pause the video and give that a try. Convert 5 minutes to seconds. Okay, so we have minutes in the denominator. We multiply by 60 seconds, because there are 60 seconds in a minute. We get 300 seconds. So it takes her 300 plus the 40 seconds to complete the run. Okay, so that's 340 seconds. So the total time is 340. So we divide 1,600 by 340, and we get 5.3. Our units are meters per second. Okay, so notice that speed and velocity here are not the same. Velocity relies on direction. It's the change in position over time. Speed does not. Okay, so we're going to head down to number 21. Okay, in 21, we have a constant acceleration type question. Okay, the reason why we know that is because of the second word here, drops. So Brian drops his cell phone from a bridge, and it strikes the water 5 seconds later. Again, with these, it's usually helpful if we draw a diagram, just so we can imagine what's going on, and we can label our variables. So Brian drops his phone, and it strikes the water 5 seconds later. He's having a bad day, Brian. We need to calculate the speed at which it strikes the water. So we want to figure out how fast it's moving. Yikes, when it hits the water. And we also, in part B, we want to figure out the height of the bridge. Delta Y. So how high did he drop it from? I think an iPhone, you can drop it from a meter. I guess it depends on how smart or new your phone is, but we want to figure out what this height is. Okay, so if the phone is dropped, we now know the only force acting on it is the downward pull of gravity, right? So we're talking about free fall here. Type 1 free fall. You head to that equation sheet, again, under your homework list. It'll list for you what assumptions we make. If it's dropped, we say the initial velocity is 0. If it's dropped from rest, okay, and if it's type 1 free fall, we say that down is the positive direction. So our acceleration rate would be a positive 9.8. Running out of room here. Oh. Sorry guys, my computer goofed for a second and erased my diagram. So it's a different color, but same pieces of information. So initial velocity is 0 because it's dropped from rest. If it's dropped, it's type 1 free fall. So our acceleration is a positive 9.8 meters per second squared. We want to find the velocity in which the phone strikes the water with, given this time. So we have initial velocity, acceleration, time. We want the final velocity. So we're looking for the equation out of the big four equations, because acceleration is constant. We're looking for the equation in which we can solve for v. Okay, specifically, we're looking for the equation without delta y in it. And that would be our first equation. So our velocity is equal to the initial velocity plus the acceleration times time. We know the initial velocity is technically 0. So we're going to have 9.8 meters per second squared times 5 seconds. One of our seconds will cancel out. We'll be left with just the units of meters per second, which is exactly what we expect or should find. And we get a whopping 49 meters per second. Is the velocity of the phone when it hits the water. Yikes. Brian's phone's not going to make it or recover from that fall. Okay, let's see how high he dropped it from. So now we're looking for delta y. Okay, if you take a look at our big four equations, we need to find delta y. We have v, v naught, a, and t. So we can really use pretty much any of those equations to solve. I'm going to use the equation in which delta y is manipulated for, just because it's a little bit easier. So delta y is equal to initial velocity times the time plus 1/2 times the acceleration times t squared. Our initial velocity is 0. 0 times t is 0. So this whole segment here is going to become 0. We then have 1/2 times 9.8 meters per second squared, which will get 4.9. We multiply those two. Sorry, that looks more like a 19. This should be a parenthesis. Times t squared. Do not forget to square the time, which is 5 seconds. So 5 squared, we get 25 seconds squared. Okay, we multiply straight across. So I'm going to have 1/2 times 9.8 times 25. And we get 122.5. Okay, our seconds squared will cancel. And we're left with just meters. Okay, so pause the video and try number 22, which is also a free fall example. So pause the video and give number 22 a try. Okay, so please check your answer for 22 with that posted in Classroom. If we have questions with 22 or a couple from the first 3 sections that you were also asked to try by yourself, we will talk about that on Monday or Tuesday regardless, meeting whichever class you're in. So if you're in A day, we'll talk about it Monday. If you're in B day, we'll talk about it Tuesday. So we're going to head back to number 19. Okay, so we have a baseball thrown at an angle of 33 degrees above the horizontal. So we see that angle here What that means is that we are talking about vectors. Man. There we go. That's better. Vectors.